Hello and welcome to this Oasys GSA webinar on footfall analysis. If you can't hear me, please check your audio settings in your GoToWebinar control panel. Make sure you got it set correctly. If you can hear me, congratulations. My name is Peter Debney. I am the Oasys Structural Application Specialist and Support Manager, and I'll be taking you through the theory and practice of footfall analysis with GSA. So, footfall, what is it? It is human-induced vibration. Footfall is prediction of how lively, how bouncy and resonant and so on a structure will be when people walk on it. Dangers of and problems of structural vibration have been known for a while. Earthquake damage, wind-induced torsional failure of Tacoma Narrows Bridge, and so on. These are all ultimate limit state problems. What we're interested in is serviceability limit state problems. Vibrations which cause discomfort on offices, on stairs, operational problems such as in laboratories and hospitals. Small-scale vibrations which aren't going to break the structure but are going to make it not work right. So vibration basics first of all. When people walk on the surface, on the floor and so on, it creates an impact force. People tend to walk at a given pace. The frequency of these impacts can set up resonances in the structure, working with resonance with the natural frequency of the structure, causing it to vibrate and shake and so on. And there's also transient effects. Momentary vibrations from a footsteps. There have been a number of design guides looking at these problems over the years. One of the first was the American Institute of Steel Construction, or AISC's guide, Floor Vibrations Due to Human Activity, published way back in 1997. Since then, there's been a number of further design guides published. Concrete Centre's CCIP 016, a design guide for footfall-induced vibration of structures. The Steel Construction Institute, or SCI's guides, P354, design of floors for vibration. And recently, the AIC has updated their design guides based on the Concrete Centre and Steel Construction Institute's guides and other research over the last 20 years. Now, some guides include simple methods for estimating the footfall response, which you can do by taking a standard floor which is closest to your actual structure, calculate the first two frequencies, then calculate the resulting velocities, accelerations, and responses. Now, these have a number of assumptions built into them, and it's difficult to make them match up with the majority of real structures, and they've also been shown by a number of sources to be unconservative and inaccurate in their results. So please note that many other programs on the market only use a simple method, which means their results are unreliable. On the positive side, the formula there, the natural frequency, fundamental frequency is 18 over the square root of deflection, is quite a useful check to see that your model is giving frequencies in about the right ballpark. So it is worthwhile doing, but only as a check to the finite element model, which is recommended by all the modern design guides. Now, this FE approach requires the analysis of a subframe in the case of a floor, or the entire structure in the case of a stair or a bridge. The first stage is to find the vibration modes and the corresponding frequencies up to a cutoff point. What that cutoff point is depends on the design guide they're using and the respective maximum walking frequencies and the fundamental frequency of the structure in question. So when the structure vibrates, it doesn't vibrate with just one mode, and the mode being the vibration shape and frequency, but with several modes simultaneously. And these modes interact to produce complex movements, such as you can see in the video. And well, you can see the vibration modes of the single beam are relatively simple. For a floor plate, they're more complex. And when you have calculated the frequencies from the vibration modes, you then need to do a subsequent analysis to calculate the velocities, the displacements, the accelerations, and so on. The accelerations might then be in terms of the peak acceleration, or root mean squared, or root mean cubed, and you might express them in meters per second squared, or percent g. And similar velocities might be in terms of meters per second, or MIPS, and so on. Look at your design guides for the recommendations of what it wants from the analysis. Acceleration is the aspect we are interested in for addressing people comfort. Their perception of vibration and whether it is a concern or not depends on what they are doing and their orientation. People standing and walking about are least sensitive, and they're most sensitive when lying down. And you'll note from the ISO base curve on the right hand side, for the limit of human perception, that we are least sensitive to very low and very high frequencies, but most sensitive in the range of 4 to 8 Hertz. These are apparently the frequencies that our internal organs resonate at, which is going to be uncomfortable. Unfortunately, this is the range that floors also typically vibrate at. Now, the AIC guide says you can conservatively just take 0.5% of G for office floors. The other design guides recommend using a weighting curve to adjust the frequencies, depending on how sensitive we are to them. This is the WG curve, which reduces the effects of the very low and very high frequencies, which is the mirror image of the ISO baseline curve. And GSA includes this weighting curve and the other standard ones. And when you adjust the accelerations by the weighting frequencies and compare it to the baseline curve, we can then see the response, or R value. So R value is as an acceleration divided by the base curve. So if our accelerations are the same as the base curve, response value of 1. If they're twice the acceleration, response value of 2, and so on. The response of footfall is not just dependent on the frequency of the floor, but also the mass, or to be more accurate, the modal mass of the vibration. Keep it simple. The modal mass is essentially the mass of the structure that is moving in a vibration mode. For example, a large span can have a low natural frequency, but it will also have a large modal mass to resist the footfall force. Force equals mass times acceleration, or acceleration is force divided by mass. More mass, lower acceleration. Thus, a low frequency floor can have a low response, but not necessarily. It might still resonate. Similarly, a short span can have a high natural frequency, but as it has a low modal mass, the resulting accelerations can be high. In other words, a high frequency floor can have a high response, but again, not necessarily. You have to dig in deeper beyond just the frequency. Now, I mentioned resonance. What is resonance? This is when the vibrations build up over time. Take an example where a floor vibrates with a particular frequency. If that frequency is the same as the walking speed, each footstep will push the floor more and more, increasing its amplitude and acceleration. This is called the first harmonic, when the footsteps are totally in sync with the floor. What is more likely, because design guides eliminate or won't let us have floors vibrating at the same frequencies as footsteps, is we might interact and resonate with every other cycle of the floor, the second harmonic, causing resonance. Then with every other bounce, or with the third harmonic, every third bounce, or the fourth harmonic. Now, I've heard a fallacy that says you need multiple regular bays to build up resonance. This is not the case, because vibrations over multiple bays tend to have a large modal mass, which lowers the response. In fact, isolated bays that do not interact with the rest of the structure can have a high response, as I mentioned, because it's low modal mass. Now, what is important here is the physical width of the mode, and thus how many footsteps can fall in that location. How many footsteps do you get as somebody walks across their area? Now, if this resonance was unchecked, the induced vibrations would eventually destroy the structure, a bit like Tacoma Narrows. But thankfully, structures have imperfections in them that can absorb the vibration energy, and we call this damping. You often hear the expression critical damping in vibration engineering. This is the figure or level of damping where the structure returns to its original position in the minimum time after the movement. More damping than this slows the return to the starting point. More usually less damping means the structure can overshoot and thus oscillate. So with no damping, the resonance vibrations will be huge. Where the natural frequencies of the structure coincide with the forcing frequencies, then again you get a large amplification of the structural movements. And how much this actually happens depends on the structural damping. Now, the damping factor of a real structure tends to vary between about 0.3% to about 4.5%. And it's depending on the construction and fit out and so on. Now, the resonance occurs not just with the fundamental, but also the harmonics as well. And here we can see a huge amplification occurring when the forcing or walking frequency is the same as the structure. This is why we ensure that the floor natural frequency is higher than the maximum walking speed. So, as the fundamentals need to be above the walking speed, let's remove that resonance and look in more detail at the harmonics. Note that the second, third, and fourth harmonics are resonated, but also the fifth and sixth and so on to a diminishing amount. We don't calculate these ones because as human walking speeds are not that constant, it's very difficult to resonate with the higher frequencies. And in some situations, we might only take the first 1 or 2 or 3 harmonics. It depends. The design guide will state how many harmonics you need to look at for particular situations. As well as resonant responses, you can also get transient or impulse responses, which is normally on high frequency structures, where the vibrations die off before the next footfall lands. Thus, it's the first peak acceleration that is calculated, and the damping has little effect on this result. To find the accelerations, we also need to calculate the force that each step generates. Now, not all the weight of the walker is translated into a force on the floor, and the design guides have recommended dynamic coefficients for calculating these forces, which you see also relate to each harmonic. Now, these dynamic load factors can vary based on different activities: walking on the floors, walking on stairs, running, rhythmic activities like aerobics and so on. GSA includes the standard dynamic coefficients, but you can also add your own as needed, which do as follows in the dynamic load factor table. That's probably a bit small for you. Let me enlarge that. So you can see that because we're looking at harmonics, which are multiples of the base frequencies, we only need to add these once. So you see 1.6 to 2.2 in this instance, and the higher harmonics are multiples of those. We just then put the load factors in with the varying values. These are constant, but they're not always constant. If you look at the design guides, you'll see there's a variety of different load factor shapes you can get. You don't need to add these, but if you do, they are included in the analysis drop-down list. You can see all these sort of standard DLFs which are included with GSA, plus the extra person walking one at the bottom there, which I've added manually. course, before we can analyze the model, we need to build it. Note first that we need to model both the beams and the slabs for a steel frame. Of course, the whole slab and so on for concrete. The mesh density needs to be sufficiently high to get accurate results. So typically we need 8 to 10 nodes in a major span. Note also that the strains are very small with footfall vibrations, which means we can model shear and pin connections as if they're moment connections. Similarly, we need to offset or can offset the beams and slabs to generate composite action, even if the beams are not designed as composite in the ultimate limit state. The strains are so low in between the beams and slabs that often they will act compositely for footfall vibration. Now, unlike the other guides where we would offset the slabs to the beams, the AIC guide recommends you explicitly determine the composite section for each beam. Now, this does allow you greater control over the stiffnesses, such as the increasing stiffness of edge beams and so on, and you don't have to compromise on the neutral axis of where the composite floor is. But you do need to calculate and supply lots of variance of each section size in your model. And we'd use a perimeter section to define these. Now, and obviously based on the modular ratio. Now, do watch out that the self weight of the slab is not overcounted in these situations, because obviously the slab is both on the shell elements but also in the beam elements. It's good to include the columns because they add stiffness to the floor. Model them full height to the next floor and fix the ends, or half height to the next floor and pin the ends. The choice is yours. The results are similar, though not identical. Now, you don't need to include multiple floors unless you expect definite sharing of vibration between the floors. Generally, the floors will act independently. You can include the stiffness of 4 partitions on the floors as nodal frame stiffnesses, or maybe explicitly model them as shell or plane stress elements. Alternatively, you can just pin the nodes in place. Each design guide has its own recommendations. Loading, you've got to include the minimum credible dead load and the design guide's recommended live loads, because these loads are then converted into mass, and mass resists accelerations. So a low mass is actually more conservative, which is other way around to the normal static analysis. To model the slab properties, we have a couple of options. First is to assume isotropic behavior, model the slab full thickness, and use the property wizard to set up the properties based on the profile decking, as you can see in row 1. And we can use a standard dynamic concrete for this. Dynamic concrete tends to have a higher Young's modulus than normal concrete. The second choice is to model the orthotropic behavior of the slab on profile decking or hollow core planks and so on. So here we model just the solid part of the slab above the decking, and then give it an orthotropic material that increases one of the directions, the span directions, to account for the missing structure. To calculate the effective stiffness or the increased Young's modulus in the slab's span direction, we can use the formula from the SCI design guide to boost the Young's modulus. Okay, and now let's take a look at GSA in action. And here we have GSA, and what we're going to do now is open up a model, this steel frame model, which is based on the sample model supplied with software. I've tweaked it a little bit, removed some of the analysis cases and so on, so we can recreate them. So here we are on the design layer, switch over to the analysis layer, and we see we have the model already set up with offsets and so on. Color by property. What are these values? Well, let's have a quick look. So material wise, obviously we've got steel and concrete, but in the material property section here, I've got a damped steel, a steel with a damping value, and likewise a damped concrete, because we can now choose to calculate the modal damping if we want to, but also the damped concrete, the elastic modulus is set much higher than normal. We go into the section properties. We can see we use the grey, we're also using the damp steel override if we want to. And if I open up one of these beams, we can see the catalogue section, but we have got the offset applied in the section profile. There's no need to set that on the elements. The column section here is obviously not offset. Similarly, on the section property, slab properties, open this up. We've got a rib deck which we activate through this section here, and we've also got the slab set out to the bottom, and the other properties will be calculated automatically. I'm just going for an isotropic slab at this time. Okay, loading. We have face loads already set up directly onto 2D elements. Call it their property references. So PA1, any element of property area 1 will have these dead and live loads applied. We've not included gravity loads. We don't need to for the modal analysis. That will calculate itself very automatically and will actually ignore the gravity load table. And in terms of restraints, we see we've got the half height columns with pin ends. Also on the plan view, we see I've got edge restraints in the Z direction, but also in the Y or X direction as appropriate to represent the edge cladding. Right, now let's set up some analyses. I'm going to run a new analysis task. I'm going to ask for a modal analysis. Now, how many modes do we need? Don't know at first. I'm going to ask for just one mode and see what frequency that gives us. What we do also need to set up is the mass derives from loads. So I'll go dead and line, double clicking to add them in, and take 10% of the live load. Analyze that. And we can then see that if I go to the global results, dynamic summary, yeah, the frequency is 6.97 Hertz. If we're using the concrete center method, that says go up to 15 Hertz for resonant results and twice the fundamental for transient. Should be 15 and 14 Hertz. In this case, 15 Hertz will suffice. So let me delete those results. Call the task back up again. And let's say I'm going to have 10 modes, but I have an upper cutoff of 15 Hertz. So it might calculate modes above 15 Hertz, but we're not interested in them. We don't need them. And finish. It's finished. No warnings, and we can see at 10 modes we've only got 6 modes used. What were these modes? Bring the summary back up again. Should left it open. And 7 Hertz up to 13 Hertz with various values. All right. Okay, let's quick check of the results. Mode 1. Look at the shape. See that there. Look at the 2D resolved displacements, and we can see we've got mode there, mode 2 in the end bay, nickel bay, mode 3, mode 4, mode 5, and mode 6. Now, if you want to see how whether we've got enough modes in terms of picking up all the parts of floor, which can have a problem with larger floor plates, what I like to do is create a combination case of envelope of those and call it modal envelope, and look at the modal envelope. Well, I should switch the shape off because I always get confused. And we can see that we've got all the pretty much peaks of interest. There's some zones here which maybe might require high frequencies, but unless that's particularly crucial, maybe we can get away without looking at those. All right, so I'm happy with the modes. Let's do a footfall analysis. Now, I mentioned about dynamic load factors, so we do have some example frequency weighting curves already in here. So I just open up one of them, and you can see there's a example frequency weighting curve, but we don't actually need these. And likewise, we can set up dynamic load factors as discussed. Right, so let's just go and create a new footfall analysis. It uses the modal analysis we used earlier. We can look at self-excitation, so the footfalls measuring the response at the node where the footfall lands. This always gives you the peak values, but it doesn't necessarily give you the full picture of one area or another. Full excitation, rigorous, that is the definite requirement for submission, final calculations. And intermediate wise, whilst making sure the analysis works and everything, we can use a full excitation fast, which includes self-excitation and take some shortcuts to the rest. A model, a full size model, this can take several minutes or longer. A model this size, not a problem. We can choose to limit which nodes are excited and measured at. If we have some lists of nodes in here, so actually we've got here some on the floor, we can just excite certain nodes. So if you're modeling a staircase, for example, you wouldn't have somebody walking on the handrail. Maybe not in the general case. So we can leave those nodes off. Numbers of footfalls, how many footsteps will land in a particular mode zone. 100, quite conservative. 10 in the model the size might be more reasonable. Yeah, measure it, engineering judgment, and so on. Mass of the person walking, direction response, weighting curves. So here's the standard supplied weighting curves. You can add your own. Excitation forces. There's the number of standard design guides. Walking on floors, on stairs, and so on. I'll choose the concrete center methods, and we see we've got the walking frequencies, extreme range 1 to 2.5 for CCRP16, walking on floor P354, 1.8 to 2.2 Hertz. Put that to concrete center. Damping values, 2-3%, whatever the damping should be, but you can also have a number of other options. And let's analyze that. Nice and quick. And look at the results. So we now have a footfall results, which we can find. So we can look at the nodal contours. For example, look at the those nodes are not very useful. Right, right, so let's produce a footfall analysis on this structure. So I'm going to add a new analysis task. I'm going to go for dynamic response footfall. The mode analysis uses, well, we've got one here, but you could have a number of modal analyses to choose from. Self-excitation or full. Self-excitation always gives the maximum value. Full excitation gives you the full picture of effects of one area or another. If you're doing a large model, making sure the analysis works and so on, you can do a fast analysis, not fully accurate, but you can check to see things are working well. A model this size will be fine. A full model can take several minutes or more. Response nodes, excitation nodes. We can choose which parts of the model if we have saved lists in here, lists of nodes. We can say which parts of the floor are response, which ones are being excited. So these could be the same areas, could be different. If it's staircase, just the treads. Operating theatre, we might say what's the effect, excite the corridor, and the responses to the operating theatre, and so on. Number of footfalls. How many footsteps will occur in a given mode? 100 is conservative. Might be 10, might be more, might be 20. Set the value according to your structure. Beside the walker, direction, weighting curves, WG, excitation forces, walking floor, center. So if I look at the center, walking frequencies are 1 to 2.5, SCI 1.8, 2.2. Design guys don't go outside these values. I'll keep it at the concrete center method. Damping 2%, 3%, whatever it should be for your structure, with some other options that we can use. Let's analyze that. And okay, that's calculated. Got some results already. Let's have a look. So we can see in the contours nodal results, footfall induced vibration, resonance response factors with the various velocities and accelerations, and the critical frequency transient responses where they occur. Now, these nodal results are good, but we want to see make them easy to read. The nodal results on elements. For example, if I go over max response on elements, we can see we have contours, which is a bit easier to read than just the nodal results. Now, GSA's calculated the separation automatically. We can force these values. Typically, the footfall values come in sort of powers of 2. So I'm going to specify contours and say 0, 1, 2, 4, 8, 16, 32, and leave the top one blank, and say OK, and OK to that. We can see the areas where it come in the standard bands, and some is in the 8 to 16. Maybe that's okay, maybe not. If it's not, we can start looking at increasing the slab thickness, adding beams and column props. Anyway, various things we can do to adjust the footfall values. What else we do? We can look at the worst case results. So we can see it's about 16 or so. Let's have a look. Say node results. Footfall reduced summary. I right click on say I'm going to the summary of the summary, and we can see that node 251 is a factor of 10.7 for resonance. Node 319 ran transient 5.7. Let's just adjust this so we can see. Let's find these nodes. So I'm going to find those nodes. Find nodes 251. And we see it's that spot there. Resonance and 319 as well. Maximum resonance, maximum transient results. Apart from the contours and general results we get here, we can also get chart views of the footfall analysis. So I'm going to ask for the footfall resonant results for node 251. Say OK to those. And these charts then show us, for example, which modes contribute to that value. Mode 2, very much dominance, a little bit to some of the other modes, but not a lot. Mode, if we want to reduce the response at that node, we could tackle mode 2. Dynamic load factors, and you can see this is from the code, and they're not but they are these shapes. This is standard results from the design code. We can look at forcing frequency versus response, and my personal favorite, walking frequency versus response, and we can see here that we're getting a peak at about 1.9 hertz. That I'll cursor at the nearest point. 1.9 2578 hertz at value of 10.6. And this graph is quite useful as well, because if we say, oh, we've got a high response, what happens if we say actually the walking speed is not 2.5 but 2.2? Will that help? No, not in this case. It would say this is not the peak value. If we are, this curve's further up, then yeah, maybe it will be. Having a lowest walking speed of say 2 hertz, yes, that would make a difference to the reported result. Similarly, we can get the transient results. Node 319. And again, we can see the modes that contribute. Mode 4, a little bit mode 3, the larger ones. And we can see the transient results as they reduce over time. Now, the transient response versus walking frequency, that always increases, not quite linearly, but if you've got a high transient response, justifying a lower walking frequency will give you a better value. If you want to assess an existing structure, then you can download the Arup iPhone app, which uses the phone's accelerometers to measure the real structural response. Expedition have also produced a similar app for Android users, and there may well be others. Now, does anyone have any questions or would like to learn more about GSA? Please write them in the questions box there in the GoToWebinar control panel if you're watching live, or email us by responding to the GoToWebinar messages, or use the addresses there on the screen, and we will get straight back to you with the answers. So thank you very much. Thank you for attending, and goodbye for now.